So yeah, I'm going to be giving an opinionated intro to NLP. Opinionated means like it'll be what I think is important, not how people usually introduce this material. Okay, so just quick grounding, what do these letters mean? They stand for natural language processing. I personally don't find that to be a very informative phrase. So I usually tell people it's machine learning on text data or text analytics. This phrase came from a subfield of computer science, which is why the word natural is there. Because to a computer scientist, language means code. So they put natural there to indicate like human languages like English. But for the rest of us, we might as well call this language processing. Another theme in the name of this is that some people are moving towards calling this natural language understanding. As far as I can tell, this is just new branding. There was some criticism, I think, some years ago about, oh, this AI, these models, they don't understand anything. So some people's fix to that was just change the name of the field. But as far as I can tell, it's not like any new way of thinking or new tools, just new paint. Oh, and I should also say that like this phrase came out of computer science, but they often use tools from linguistics that, you know, like is an entirely different field that goes back much further. Okay, so I thought it'd be more fun to start with a demo. I have nothing to do with this demo. This is from the Allen Institute of AI Research Institute in Seattle, founded by Paul Allen, one of the co-founders of Microsoft. I find them to be a really good place to just get a feel for what the state of the art is. They do have like a Python library, which I think is a bunch of like their research tools and infrastructure that they made into an open source library. I personally have not used it very much. It kind of like deviates from other standard APIs in some strange ways. But yeah, I think it's like a good place to just get a feel for what problems are like they're trying to solve and what the state of the art is. But definitely when you put things into production, it won't perform as well as in research. Yeah, so this is their demo. I'm just going to show a couple of these different problems to give you a flavor of like the problems that they're trying to solve, right? So for each of these, named entity recognition, I'm starting this one because this is one I've been thinking about a lot lately. This is a problem where you try to pull out the names of people, locations, and organizations. So like basically like proper nouns. Those are the big three. Sometimes people generalize this to the names of products because that has a lot of business value these days. So each of these has some stock sentences that they give you. I'm not going to deviate from them, but you can imagine, you know, trying to trick the model by putting in your own sentences. Okay, so just to show you what the model does, right? This shirt was bought at Grandpa Joe's, which is recognized as an organization. Companies are considered organizations in downtown deep learning, which is recognized as a location place, even though that is probably not the name of an actual town. Yeah, so that's an example of what that does. Another one that is really popular is sentiment analysis. So is this sentence positive, negative, or neutral? And the reason that this is so popular is because there's just like a lot of free web data about this. So like all of Yelp or IMDb, like anything that you do like thumbs up or thumbs down or like a 5-star review, like it's really easy to scrape that data in that text and then build a classifier off of that. So to run an example. Yeah, so a very well made, funny, and entertaining picture. The model is very confident, there's probably some score under there, that the sentence has a positive sentiment. People do try to do more fine-grained versions of this, like not just positive, negative, neutral, you know, like happy, excited, anxious, sad, but that just gets more difficult. Another one, reading comprehension. So this is you put in a piece of text, like usually something from a textbook, like a paragraph from a textbook, and then a question. And it is known that the answer to the question exists in the text. And the model tries to find the answer to the question. So in this example, how many partially reusable launch systems were developed. It finds 2 partially reusable launch systems were developed. Right, so you could see a little bit how the model gets some hints there. The last one I want to show, I don't know a lot about this problem, co-reference resolution, but I find it really impressive that people attempt this at all. It's where you have like a person who's named and then they're referred to later on, like who does he refer to in this sentence? And I feel like this is hard for people too. So it's amazing to me that people attempt this. So this is an example. Yeah, so there's like a paragraph here and you can see some named entity recognition has to run first, right, to find these people names, right? So these building blocks, often you use them together, build them off of each other. And so there's like Paul Allen here, and then later this he refers to Paul Allen as opposed to Bill. Yeah. Yeah, so those are just like to give you a flavor of the problems that people try to solve here. Another thing I wanted to share was when I first saw this reading comprehension, I thought it was a different problem, which I want to share about because I think there's like a trend around it. And that is you can take a piece of text and try to classify its reading level. So is this like an elementary reading level or high school or college reading level? And I think like textbook or exam prep companies have pumped a lot of money into this problem in the last few years because they're trying to like automate the writing of standardized exams or perhaps automate some of the scoring of standardized exams. Okay. So those are some of the problems. How does it work? Okay, so this is going to be a very simplified explanation with a focus on the parts that I think are important. Okay, so this is a simple architecture to predict the part of speech of a word. So you have the word dragons and you want to predict, is it a noun, verb, adverb? Here kind of, the illustration is, oh, it thinks it's 92% likely to be a noun, 1% likely to be a verb. Of course, like usually you would have a sentence or a paragraph. I didn't want to get into the hairiness of like splitting a sentence into words. So I just started with a word here. But what I want to emphasize is that there are 2 parts to this problem, standard machine learning and what I'm calling the heart of NLP. Okay, so let me start with standard machine learning and then tell you why it's not going to be the focus of this talk. So standard machine learning is just, you have a bunch of numbers as input data and you want to make a numeric prediction, right? So numbers in, numbers out. For example, let's say like you have an accident, a car accident with 2 cars, right? And you know like the speed and velocity, or like the velocity and the direction of car 1 and the velocity and direction of car 2 and like the weights of the cars, right? You have a bunch of numeric data in and you want to know like what type of accident was this? Like, was this like to be like a T-bone or a rear end or a side swipe or what type of accident, right? So either way, it's like numbers in, numbers out, right? And so there are tons of machine learning tools to deal with that. What makes text really special is that you don't get to start with numbers. You have to start with text and you have to somehow figure out what numbers should I use, right? And so for that reason, I really like working in this area because I think there's a lot of space for creativity. Okay. Yeah, so this is just an example, like to say, like you could spend like a Saturday afternoon thinking about like, oh, here's a piece of text, like what number should I associate with it? Like what would be useful, right? So there are like simple ways to do this and like complex ways to do it. And often like the simple ways like work pretty well. So you know, I would not be afraid to jump into this area. This is a piece of text. So some background about this. Some years ago, the US Federal Communication Commission put out a proposal to remove net neutrality. And they had a period of time that was open for public commentary. And so lots of people gave comments in support and against the proposal. But then there was some concern that a lot of the comments came from bots. So there was some NLP efforts to try to figure out which comments came from people and which comments came from bots. And so this is just a sentence from one of those comments. I don't know if it's from a person or a bot. I don't know if this is an easy problem to solve or not. But I just put the sentence here, given that problem, like, just thinking like what numbers could you extract from this text that might be helpful for figuring out if this is from a bot or a person. So now I'm going to do like a slightly uncomfortable thing and like pause for like 10 or 15 seconds to give you time to think about that. Okay, I don't know. Are there any ideas anyone wants to share?
Something to do with grammatical, like nouns, verbs, like classifying the words.
Yeah, the number of nouns or verbs.
Fraction of caps
Deliberate.
versus lowercase.
Yeah, and how they're
Yeah,
tied
definitely.
to particular themes that are being pulled out, like the call to action and the overall like topic.
Yeah, maybe if we have like words that we know that fall under certain topics, like the number of words in each topic.
I think you could probably look at like syntax, like n-grams, like if you have like noun, verb, or like whatever particular repeated grammatical structures.
Mm-hmm. Yeah, so these are a couple that I was thinking about, right? Like there's the one about the ratio of capitalized words, because I thought maybe a bot wouldn't write a word in all caps like that. That seemed like a human thing to me. The ratio of like common everyday words, or maybe like words under a theme, to uncommon words, because I don't know, maybe bots write in simpler language. The number of punctuation marks. This sentence doesn't have an exclamation point, but I bet people use exclamation points much more irregularly than bots do. Oh yeah, and then the number of words is usually a useful thing to throw into there. Yeah, so you can think a lot of these are counts. I guess actually some of these are ratios. But very quickly you move into the space where you need to normalize the counts. Generally because two pieces of text might have the same meaning, but one text is much longer than the other, or like one person was just more wordy, but they were saying the same thing. And so very quickly you move into the need to normalize. So the most common normalization is called TF-IDF. I'm going to spend the next slide talking about it. This is where if you like open an NLP textbook, like most textbooks start, but it's like really difficult to start with like a talk with a box of numbers. And so this will be the only slide, I think, with a box of numbers. Okay. So one of the reasons I thought it might be interesting to talk about this is because I think there are a lot of engineers on this call. And so I don't know a lot about this problem, but I think it's not solved like how to do this efficiently. These things tend to take a lot of memory. Okay, so the problem setup is that we have a bunch of documents, for example, 5 documents, and we want to make this matrix, this box of numbers. And so we have a column for each document, D1 through D5, and then we have a row for every word that appears in any document. And then the number that appears in the box is just the number of times that word appeared in that document. So complexity appeared in document 1 2 times, and algorithm appeared in document 4 4 times. And anywhere there's not a number, it's a 0. And in fact, this matrix will have a lot of zeros. It's very sparse because most words don't appear in most documents because we don't use all the words we know at any given point of time usually. Yeah, so creating this matrix or like using it generally takes a lot of memory. And so you can see, to tie this back to before, why is this a vectorizer? So for each piece of text, for each document, we're trying to create a list of numbers, a vector, right? So here we have the counts, right? So this is a count vector. It counts how many times each word appears in document 1. But like I said, we needed to normalize, right? So this is already the TF part. This is already the term frequency part. The normalization is the IDF, inverse document frequency. So you do the same thing for each row. You count the number of documents that the word complexity appears in, and then you divide each number by that. So complexity appears in 4 documents. So this becomes 2 over 4, 1/2, 3/4, 1/2, 3/4. And you do that normalization because if there's a word that appears in all the documents, then that like isn't a very special word. And it doesn't tell you, what's special about this document or this subgroup of documents. And so you want to normalize that out. Oh yeah, that's just some text to describe what I just said. Another thing to note is that these are some pretty simple functions. Like you have the term frequency and you have the inverse document frequency. You could like apply a log function to the term frequency and then multiply it by the inverse document frequency, or you could like apply a sine function or something else. Nobody does sine, that's not useful. But there are many things you can play around here to try to get different utility out of this. Log helps out a lot. There's like a Wikipedia page that describes the ones that, through experience, people have found to be useful. Okay. Yeah, just to touch briefly back into reality, what we're trying to do is for each text, come up with a list of numbers, right? So the next slide will be another, like a totally different way of doing that. So this is kind of very traditional NLP. So the reason like this stuff is popular now is because people are creating these vectors through neural nets. I think the first one was called Word2Vec, came out from Google. The latest and greatest also happens to be from Google, called BERT. They kind of like to name their neural nets after Sesame Street characters. So there's also Elmo and Grover. But in general, like this needs a lot of big data, like, most of the digitized New York Times or something like that to build. So as practitioners, mostly we just download these assets and figure out how to use them for our applications. So how these vectors come about is a little bit subtle. So the answer won't be there right away. So going back to that part of speech model, right? You have a piece of text and you want to predict the part of speech of each word. That's a very actual like human labor intensive task, because somebody has to go through and say, this is a noun, this is a verb, this is an adverb, right? And so you have to either do that yourself or you have to pay someone to do it, right? So this is a very expensive data set to build. So you could ask yourself, like, what are prediction tasks that I could come up with that don't require a person to go through and label all the sentences? I'm gonna pause for a moment. So one task that doesn't require anybody to read anything is predict the next word task, right? So once upon it's highly likely the next word is time, right? And this doesn't require any person to go through, is because you could just, automatically scrape a bunch of text, split it on sentences, split it on words, and then just mask out the last word and tell your model, oh, predict that last word, right? So it doesn't require you paying anyone or you taking a bunch of your own time to label these sentences. To generalize that idea, you could just mask out a random 10 to 20% of the words and automate the creating of this training data, basically. And this is a really powerful idea. I think this is the reason this whole area took off, because nobody had to go through and label all the sentences from the New York Times. So this is a prediction task. What we're actually trying to do is get a vector, right? So now we need a list of numbers. So where is that list of numbers? To understand where that is, it's because this box is a neural net. I'm going to give a very bad explanation of what a neural net is. It's a series of operations where in each operation, you put in a vector and you get out another vector. So it's just a bunch of things where you put in a list of numbers, you get out another list of numbers. You take that list of numbers, you put into another thing, you get out another list of numbers. So most of these things are multiplication, like dot products. You can have nonlinear functions like sigmoids. You can have like wildly non-deterministic things, like you take the list of numbers and you randomly drop 20% of those numbers. Sometimes people do that to increase the randomness and to prove training. You could take the list of numbers, you could take the maximum of those numbers. So you put in a list of numbers, you get out another list of numbers. It might not be like the same length, right? But that's okay. So basically what this vectorizer is, it's a stack of operations where you put in a vector, you get out a vector, right? So there's tons of intermediate vectors in here. And so this is like more art than it is science, but you just pull out one of those vectors and you use them. And people generally say, like, there's a lot of agreement on this. You should use one of the later ones because the earlier, I guess, the text hasn't been processed well enough. There's not enough semantic meaning in those vectors yet. But whether you pull out, like the second to last one or the third to last one, or you take them and you add them together or you average them or whatever, that's kind of something people fiddle with. So the reason I say this is subtle is because this isn't what we set out to do, is to get these vectors. What we set out to do was to do this fill in the blank model, this prediction task, and to pull out these vectors, but so what? And the so what was in the original Word2Vec paper. I think this is like pretty widely known now, that these vectors, you can do analogies with them, right? And so that's why people started to think, oh, these vectors have like some sort of meaning. They're useful for something, right? And so I think this is like the most popular example, man is to woman as king is to queen. So when people say that these models can do analogies, what they mean is, right, so the whole thing of the vectorizer is you take a piece of text and you can associate with that a list of numbers. So you take that vector for man, you add it to the one for women, you subtract the one for king, and then up to a certain number of decimal places, you get the one for queen. And so, yeah, I think like this paper just created a lot of like attention to this area because this wasn't, what this model was set out to do. This thing just kind of happened as a side effect. Maybe this is one of the examples, where people say, we don't know what these models are doing because we weren't aiming for the side effect, but we got it anyhow. And so then like people think, well, if it was useful for analogies, maybe they're useful for other things. Yeah. So in general, most people don't, I've never trained these vectors. Usually I just download them on some like open source license and use them for some other application. Okay, so a couple of my favorite problems in NLP. This is an extremely opinionated slide. So my favorite problem is related to cross-lingual methods. So we have high resource languages where we have a lot of digitized text, and we have low resource languages where we don't have a lot of digitized text. And you can take whatever you have and create vectors, however you like. And then you can try to align those vectors in a way that you can like transfer the structure and the learning from the high resource language where you have a lot of digitized text to the low resource language, and try to create applications that extend to low resource languages from the ones that you have in high resource ones. There are also a lot of code switching or language mixing problems because a lot of people mix languages when they talk. Anomaly detection in NLP, so you can mix different subfields of machine learning together. You don't have to just monitor time series data. You could like monitor text data coming in and try to find anomalies. Semi-structured text, I think, is like a great way to get started. like really free form text is kind of hard to wrap your mind around. But if there's some sort of text that like has some structure to it, like a recipe, it's like always the same at the beginning, like 3 eggs, like number, ingredient, or like 1 cup of milk, you know, there's like some structure to that text. And so a mix of structure and unstructured, there's like a lot of richness there. And then of course there's like fairness issues, right? So this model knows how to do man is to woman as king is to queen, but is not correctly do man is to woman as doctor is to doctor. Yeah, so this is the last slide. Just a couple of resources. There's a couple of like leaderboards out there that can tell you kind of where the state of the art is at. A couple of my favorite libraries. The Stanford NLP group is really interesting. I haven't used it much, but they really mix some of these old school linguistics and like sentence diagramming with machine learning. A couple of places to get data assets. These are all also libraries. Fast text will give you cross-lingual vectors. Hugging Face is like this big repository of where it has many things, but also where everyone seems to be putting their vectors. And then Kaggle is widely used, but like I think it's a good starting place if you have a problem and you don't know, you know, what sort of text is out there. It's a good place to get ideas for like where could I find some text that would be useful to my problem. Okay, that's it.